All right, final exam scheduled for Sunday through Tuesday of this week. All the times are listed on Sign Up Genius. It's a 2-hour, no personal calculator, no notes, closed book cumulative exam. Exam will run in Google Meet, just like the midterms did. Invitations will be sent out the night before the exam. Make sure you've already signed up for a time prior to that day. The exam process says basically show up to Google Meet, have scratch paper, your ID ready, and have a clean workspace with room to position your webcam so I can see you and your work area during the exam. And a reminder, it's your job to have an appropriate space. So if you need to prepare some space to make sure you have room to kind of position your camera where I can see you in your workspace, that's important. Okay. So general exam information. Any questions there at all? All right. All right, we'll kick off the review. So we're going to cover all the course contents. Probably going to take about an hour and a half, hour to 40 minutes or so. Make sure you ask questions. There's only 2 of you in this session, so if you have any questions, feel free to chime right in. I'll also keep an eye on the chat. You can type in questions you have there as well. The goal is I'll do a little bit of review. I'll present a problem, work through the problem. If you can get through it from start to finish, you are ready for the exam. If you're struggling on some of the problems, the idea is that's going to point you in the direction where you need a little extra prep. Okay? All right. So we started this course in Chapter 1. In the first part of the course, we learned about linear systems. We learned that we could represent linear systems either with a system of equations, or a vector equation, or a matrix equation, or even with a linear transformation. And really all 4 of those were just different representations of the same thing. So we could take any system and rewrite it like a matrix equation. We could take any matrix equation and rewrite it like a vector equation. And then to solve any of these, we basically could either use row reduction, we take our matrix A augmented with B and do row reduction, or in some cases we could calculate the inverse and solve by multiplying both sides by the inverse matrix. Okay, so let's get a little practice of that. It's a core operation. So here is a system, a linear system. Go ahead and solve that linear system and write your answer in parametric vector form. And I'll give you a head start while you work through that. When you get your final answer, go ahead and type it into the chat. I'll give you a head start, and I'll start quietly working through mine. All right, I have my solution up here. So our first step was to write out that augmented matrix and then do our row operations. Remember, I'm using my first pivot value to get zeros below it. So I'm going to take row 2 minus 2 times row 1. With only that one row operation, I end up here, which is RREF form, row reduced echelon form. And from there, I can start to write out my solutions. I write out the equation associated with the first row. That is this guy right here. And then because there's no pivot in the second column, I know x2 is a free variable. Because there's no pivot in the third column, I know that x3 is a free variable. From there, I solve my equations for the leading values. I'm basically going to think of this like a matrix or a vector. And from there, I'll break it up into 3 different vectors, one for my constant values, one for my x2 values, one for my x3 values, and here is my solution in parametric vector form. Any questions about that first example, solving linear systems and writing your answer in parametric vector form? All right, that's one way we can solve these systems. Another way we could solve is by calculating the inverse matrix and solving that. Now, not every matrix is invertible, but some are. So now I have a new system. Oops, my new system, AX equals B here. And I'm going to solve this one by calculating the inverse. So calculate the inverse of this matrix and use it to solve this matrix equation. Once you get your solution, write your answer in the chat, and this time I'm actually going to wait for them. So type your answer into the chat. Calculate your inverse matrix and use it to solve the matrix equation. Type your answer into the chat. If you are stuck, feel free to just put question marks in the chat. That's also fine. Just want to make sure I've given everyone enough time to work on it. I'm going to wait for some answers into the chat. Once you get finished, type your answer into the chat or type question marks to indicate you're stuck. All right, one solution so far. Two so far, one more to go. All right, let's take a look. All right, so there's 2 ways I can calculate the inverse. I have a formula for 2 by 2 matrices that says if A is some matrix A, B, C, D, then this would be my formula for the inverse. So I would take 1 over the product of the strong diagonals, 4, minus the off product, which is 0, times the matrix I get when I switch the values on the strong diagonal and change the signs on the off diagonal. So in this case, I would get 1/4 times this matrix. It would be 1, negative 1/2, 0, and 1/4. This would be my inverse matrix. Now the other way I can calculate the inverse, the other way I would have to calculate the inverse if this was a larger matrix, a 3 by 3 or bigger, is I would take my matrix A and augment with the identity matrix. And from there I could do row reduction. After row reduction, the left-hand side would eventually row reduce to the identity matrix, and whatever was left on the right-hand side would be the inverse matrix. So those are my two ways to calculate the inverse matrix. Now what do I do with my inverse matrix? Well, I'm trying to solve this equation, AX equals B. So what I'm going to do is multiply both sides by the inverse, but I know that A inverse times A is just the identity matrix. And I know the identity matrix times X is just X. So once I know what the inverse is, I can just take A inverse times B to generate my solution. In this case, I'll have the inverse times the vector B, and we'll get the answer 1 minus 1 and 0 plus 1/2, which would equal 0 and 1/2. And that would be my solution. Okay, so I've reviewed two different ways to calculate the inverse and how we would use it to solve a matrix equation. Any questions there at all? Remember, if you have questions, chime right in. You want to get your questions answered because it's going to be your score on the exam. All right, so now we have two different ways to solve these matrix equations or vector equations or linear systems. But sometimes, if the size of the problem is big, or if it has to be worked repeatedly, in other words, you have to keep resolving it for different values on the right-hand side, different b values, we might want to answer some certain questions about the existence and uniqueness of solutions ahead of time. However, each of the representations, whether it's a vector equation or a linear system or matrix equation, has its own vocabulary about how we talk about existence and uniqueness. And throughout the course, we kind of went through each of them, and then we summarized them in this big table of information. And so here is my existence and uniqueness table. And the idea is that we have our representations over here on the left. And then if I want to talk about the existence of solutions, what would it mean for there always to exist at least one solution? Well, then we have the four different ways to kind of express that idea. In terms of a system of equations, we would say that there's at least one solution for any B1 or B2, no matter what the right-hand side is. But that's equivalent to saying that the vector equation, that these vectors span R2, or that there's at least one linear combination that yields B for any B in R2. So those two statements are the same. One way we can determine if this is true is if there's a pivot in every row of the matrix A. And then lastly, the associated linear transformation would be onto. So the idea is that these are four different ways to say the same thing, that there always exists at least one solution. So if one of those things is true, they're all true, and the easiest thing for me to check is the pivots. So then in practice, if I want to figure out if two vectors span R2, I would put them into a matrix, I would row reduce, and see if there's a pivot in every row. If I wanted to see if a transformation was onto, I would form the associated matrix, I would do my row reduction, and I would see if there's a pivot in every row. Because if one of those statements is true, they're all true. Same thing for uniqueness, right? If one of these things in the uniqueness column is true, then they're all true. And so here I would say that there's at most one solution for any B1 and B2. In other words, there's not more than one. A 0 or 1 solution would mean they're unique. We could also say that the vectors in the vector equation are linearly independent. Linearly independent vectors means there would be at most one solution. How do we tell if they're linearly independent? Well, we check to see if there's a pivot in every column of the matrix A. And lastly, this will be associated to a transformation that is 1 to 1. So if any one of those things is true, they're all true. And the easiest thing for me to check, once again, is the pivots. So to determine if vectors are linearly independent, I would put them into a matrix, do my row reduction, and see if there's a pivot in every column. Okay. So existence means there's one or infinitely many solutions. Uniqueness means there's 0 or 1 solution. And if we have a square matrix, well, in that event, if there's a pivot in every row, there would have to be a pivot in every column. So specifically for a square matrix, if any one thing is true in either column, then everything is true, and there would be exactly one solution. And that will also tell us that the matrix is invertible. Okay? So that is our big summary of existence uniqueness. Any questions for me so far? All right, let's see if we got it here. All right, so consider the transformation, the linear system, the vector equation, yada, 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 where these are the potential matrix A's. We want to write down all of the statements that are true for each matrix. So we'll start with the first one here. Write the number of each statement that applies to matrix A. And then you can type these into the chat. So maybe you think it's 1, 5, 8, and 9. I don't know. You would just type that into the chat. So for matrix A, list all the sentences that would be true, all the statements that would be true. And once again, question marks are totally fine. One response so far, waiting for 2 more. And 1 more to go. All right, let's take a look. So the easiest thing for me to pick out is the pivots. Right now I'm already in REF form, so I should be able to identify the pivots. I see a pivot here, I see a pivot here, I see a pivot here. So what I see is there's a pivot in every row, which is 3. And that tells me that all of the existence criteria is true and none of the uniqueness criteria is true. I have a pivot in every row, but not a pivot in every column. So if there's a pivot in every row, that tells me there's at least one solution. The columns span Rn, and the transformation is onto. So in this case, 1, 2, 3, and 4 would all be true. Right? If we scroll up to our list again, we basically said that because there's a pivot in every row, all of the items in our existence column are true. All right, any questions on the first one? If not, we'll move on to the second one. Go ahead and type your answer to the second one into the chat. And of course, if you have any questions, feel free to type those in the chat or just unmute yourself and ask either way. Got a quick first response on the second one. Wait for 2 more responses. Here's number 2. And we'll take a look here. So basically I see that I have a pivot here, a pivot here, and a pivot here. I do have a pivot in every row, and I do have a pivot in every column. So in this case, all 9 items are true. Because there's a pivot in every row, the first 4 items are true. Because there's a pivot in every column, the next 4, 5 through 8, are true. And if they're all true, then the matrix is also invertible. So this one would be 1, 2, 3, 4, 5, 6, 7, 8, and 9. And then lastly, once again, we identify our pivots. Here I have a pivot in every column, but not row. So in this case, there would be at most one solution. That's 5. Remember, there's no free variables, so I can't have more than one solution. In this case, the columns are linearly independent. We can see there's a pivot in every column, and that makes the associated transformation 1 to 1. All right, that wraps up our existence and uniqueness criteria. Any questions here? All right, next we're going to review some transformation stuff. So we need to be able to work with transformations. Consider this transformation that takes the input x1, x2, x3, outputs x1 minus 3x2 plus x3, comma x2. And we want to know what the domain is, what the codomain is, and then we're going to find the matrix that does the transformation and determine if it's 1 to 1 onto both or neither. When you get all the way through the problem, go ahead and write your answer to the last one into the chat. That way I'll know you've had time to work on it and I can work through my solution. All right, I'm going to go ahead and talk through my solutions. Remember, the transformation is really just like a function. It takes an input, it generates an output. I could make up an example, for instance, if I thought about the input that was 1, 2, 3. If I plug in x1 equals 1, x2 equals 2, and x3 equals 3 into my formula over here, well, I guess I would get 1 minus 6 plus 3. 1 minus 6 plus 3. That looks like a value of -2. And then we got comma 2. So -2, comma 2, if I did that correctly. So the idea is that I'm inputting a list of 3 numbers and outputting a list of 2 numbers. That tells me my domain, the set of inputs, is in R3. And the codomain is a subset, or the codomain is R2. All of my outputs live in the space that is R2. I might not be able to get to all of them, maybe I will, but that's the codomain where the outputs live. So to get a sense for what the matrix is, I like to rewrite my transformation kind of in terms of vectors. So my input is a list of 3 numbers, x1, x2, x3. That's essentially a vector. So I'm thinking of my transformation as taking this vector input and mapping this vector output. And when I write my output kind of vertically, I can almost think about the matrix that has columns representing these variables and just kind of extract my matrix over here. So it looks like my matrix is 1, -3, 1, 0, 1, 0. So in other words, if I took that matrix and I multiplied it by some vector, say 1, 2, 3, just like I use as my input up here, that multiplication would do the action of the transformation, and the result would be 1 minus 6 plus 3 and 2. Which hopefully will be my value of -2, 2, that same output. So we have found the matrix that does the transformation. Now to determine if it's 1 to 1 onto both or neither, I can once again reference the pivots. I have a pivot here, I have a pivot here. Because there's a pivot in every row, I know the transformation is onto. Because there's not a pivot in every column, I know the transformation is not one-to-one. So in this case, the transformation is just onto. Any questions here? All right. That really wraps up our conversation about transformations, and it really wraps up chapter 1. From there, we got into chapter 2. We started working with matrices. We had already learned how to multiply a matrix times a vector, but now we also added the ability to take a matrix times a matrix. We also worked with the identity matrix and the transpose of a matrix, and then eventually matrix inverses, which we've already covered here. So go ahead and take these matrices in the vector, so the matrix A, the matrix B, and the vector V, and see if you can calculate the following values. Go ahead and calculate the following values. Write NA if you're unable to do the calculation. And when you're all done, give me the answer to this one, the last one, into the chat. So I know you've had time to work through it. When you get through them all, go ahead and write your answer to the last one into the chat. All right, I'm going to start looking through my calculations. I'm going to start with A times V, and the idea is when we take a matrix times a vector, there's two ways we can do it, the linear combination method or the row vector method. The row vector method basically says take the dot product of the row with the vector. Take the first component and then do that for each of the rows. We can kind of define it now in dot product now that we're at the end of the course and we know what a dot product is. But in this case, if I want to take the dot product of this row and this column, the dimensions don't match up. So I need the columns, the number of columns of A to match the number of rows of V to be able to do the multiplication. In other words, A is a 3 by 2 and V is a 3 by 1. I need these inside numbers to match for me to do the multiplication. So in this case, I have an NA. I can't multiply those two. Now in the next one, we're taking the transpose of A. That flips the rows and columns. That means the first column becomes the first row. And now, because I have A transpose as a 2 by 3 and V is a 3 by 1, now I can do the multiplication. So I'm going to take the first row dotted with the vector to get 1 plus 0 plus 6, and then I will take the second row dotted with the vector to get 2 plus 2 plus 2. So when I do A transpose times V, I get the vector 7, 6. 7, 6. Next, I go to A times B. Matrix multiplication is just repeatedly doing matrix vector multiplication. So basically, I'm going to take this matrix times the first vector to get the first vector of the output. So in that case, I'm going to take 1, 2 dotted with 1, 3. I'll get 1 plus 6 is 7. Then I'll take 0, negative 2 dotted with 1, 3 to get negative 6. And I'll get the third column dotted to get 3 plus 3, which is 6. And then I'll repeat all those operations using the second column. I will get 2 minus 2 is 0. I'll get 2, and I'll get 6 minus 1, which is 5. So that would be my product of A times B. And then lastly, when I go to B times A, well, now if I take the dot product of the row with the column, now the dimensions don't match up, and I can't do this. And so the last one would be NA. And the note here is that AB is not necessarily to BA when we talk about matrix multiplication. Matrix multiplication is not necessarily commutative. All right, questions here about matrix vector or matrix multiplication. All right, the other big topic of beginning of chapter 2 is matrix inverses, but we've already talked about that a little bit as well. So we will move on to the later part of chapter 2 when we started talking about vector spaces. Right, so we've already worked with vector spaces like R3 and R4, but this one we started to generalize the idea of vector space. Now we said a vector space was any collection of objects with addition and scalar multiplication defined such that 10 big properties were satisfied. We had a big list of 10 properties. So some examples of vector spaces were R3. So all the Rn spaces were vector spaces, so we're very familiar with a space like R3. Now what's special about a vector space, what makes this collection of objects that satisfies proper special, is that every vector space will have a basis, in other words, some small set of vectors that we can build the entire space with. And they also have a dimension, a way we can talk about the fixed size of a vector space. So as an example, if I'm looking at the vector space R3, one example of a basis might be 1, 0, 0, and 0, 1, 0, and 0, 0, 1. I could take linear combinations of those three vectors and build any other vector in R3. And then also, these three vectors are linearly independent, so they're not linear combinations of each other at all. So this would be one example of the smallest set of vectors I could build the space with. Now, how do we talk about the size of a vector space? The dimension of a vector space is the number of vectors in its basis. So in this example, I see there are 3 vectors in a basis, so the dimension of R3 is 3. Okay, so the dimension of a vector space is different than the dimensions of, say, a matrix, is different than the dimensions of, say, a house. Same word, different meaning. Here, the dimension of a vector space is the number of vectors in its basis. Another example of a more abstract vector space is the set of all m by n matrices. So if I look at the collection of all 2 by 3 matrices, that set of objects would be considered a vector space. And an example of a basis for that might be 1, 0, 0, 0, 0, 0, 0, 1, 0 with a bunch of zeros. Here would be another 2 by 3 matrix, and another one, and another one, and one more. So if I look at those 6 matrices, I could build any 2 by 3 matrix just using a linear combination of those 6 matrices. So in that case, this would be a basis for this vector space. In this case, what would the dimension of this vector space be? Go ahead and type that into the chat real quick. What would the dimension of this vector space be? Set of all 2 by 3 matrices. All right, perfect. So a quick answer there. The dimension would be 6. There are 6 vectors in this vector space. And the last example might be the set of all continuous functions. So really the set of all continuous functions would be any function that basically you can draw without picking up your pen, right? So it doesn't have any holes or jumps in it. So you can think of e to the x, sine of x, x squared, all those would be continuous functions. Now it turns out one example of a basis for this would be 1 comma sine of x comma sine of 2x comma sine of 3x comma dot 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 forever. That would actually be the example of a basis for this space, which means the dimension of this space would be infinity. This would be an infinite dimensional vector space. So just kind of a neat example. In our course, we focused on finite dimensional vector spaces. All right. Now in our course, we really didn't focus on showing that vector spaces, collections were vector spaces by satisfying all 10 properties. Rather, we said, if we already know that we have a big vector space and we're focused on a little subset of it, could we show that subspace is a vector space by itself? i.e., that would be a subspace. To show that a subset is a subspace, we only had to check 3 properties, much easier than the 10, and these are the 3 properties we had to check. Is 0 in our subset, and is our subset closed under vector addition and scalar multiplication? As long as we can't add our way out or scale our way out of the subset, well then it would be a subspace. So here are 2 examples of subspaces. We would say the set of all polynomials of degree 2 or less is a subspace. And if we're calling it a subspace, it must live in a bigger vector space. That bigger vector space would be the set of all continuous functions. So this means a subspace of. Another example might be the set of all solutions to this homogeneous matrix equation. This matrix equation AX equals 0. This would also be a subspace. Right? We're looking for all the solutions to this equation. We see those solutions live in R3. So this would be a subspace of R3. And in fact, the second example is a pretty common vector space that we work with quite a bit, the set of all solutions to AX equals 0. What is the name of that often used vector space? Go ahead and type that into the chat. The vector space that is the set of all solutions to AX equals 0. All right, this one's going to be called the null space. The null space is the vector space that is the set of all solutions to AX equals 0. And in fact, there are 2 vector spaces that are kind of related to matrix equations. One is the null space, and the other one is the column space. The null space is the solutions to AX equals 0, and the column space is the span of the columns of A, or all of the B's you could get from the matrix equation AX equals B. So given that those 2 spaces are vector spaces, we should be able to determine a basis for each of them and the dimension of each of them. So here I have a matrix, and I have done the row reduction for you for this matrix, and you can use that to answer the following 5 questions. We want to find a basis for the null space, the dimension of the null space. We want to be able to answer the question, is this vector v in the null space? And if so, what would the coordinates of v be in terms of the basis? And then we want to find a basis for the column space and the dimension of the column space. So work on those problems. When you get all the way to the end, enter your answer to the last one into the chat. Enter your answer to the dimension of the column space or the rank of A into the chat. That way I'll know you've had enough time to work on it. All right, one answer so far. All right, let's take a look. All right, so the first one is talking about the null space. The null space are the solutions to ax equals 0. So to find a basis for this, I'm just going to solve ax equals 0. So to do that, I would augment with the 0 vector and do the row reduction. And the row reduction would turn out to be this. And then I would write my solution in parametric vector form. So in this case, the first row gives me x1 is equal to x2 minus x3 when I add the x2 and subtract the x3 to the other side. I know that x2 is a free variable and x3 is a free variable. In parametric vector form, my solution would then be 1, 1, 0 and plus x3 times negative 1, 0, 1. Right, so all of the solutions can be built using these two vectors, so a basis for the null space would be those two vectors. So because there's two vectors in my basis, the dimension would be 2. So the null space here is a subspace of R3. I can see all of the vectors in the null space would be vectors in R3, but the null space is two-dimensional, so it's a two-dimensional subspace of R3. That's what the null space is in this case. Any questions there? The next question says, is V, this vector V, in the null space? Well, the easiest way to answer that would be to just take A and multiply it by our vector and see if we get 0, 0. And when I multiply this together, I'll get 1 minus 2 plus 1, and I'll get 2 minus 4 plus 2. So I really will get the 0 vector. So it really is in the null space. Now because it's in the null space, and because I have a basis for the null space, I should be able to build the vector v using a linear combination of the basis vectors. So I should be able to build v by taking some number of the first basis vector plus some number times the second basis vector. And how much of each basis vector I need is going to be the coordinates of v in terms of my basis. Now in this case, I can kind of eyeball this one up. I could of course do row reduction, but I can see that C1 would have to be 2 to get a 2 in the second component. And if that was true, then C2 would have to be 1 to generate V. Once again, I can eyeball it up here, but I could certainly solve that with row reduction. That tells me that the coordinates of V in terms of the beta basis would be 2, 1. Remember, the coordinates are how much of each basis vector do you need to build a particular vector. Any questions so far about null space, basis, dimension, or coordinates? All right, next we're going to move on to the column space. The column space is the span of the columns. It's a space I could build using these three columns. So to be a basis, I have to have a set of vectors that spans the space and are linearly independent. So I know these three columns span, but what I'm looking for the basis is the linearly independent columns of A. So to figure out which vectors are linearly independent, I would do the row reduction. And since I identify that there's a pivot in the first column of the row reduced form, that tells me to grab the first column of the original matrix A. That tells me that the basis for the column space would just be the vector 1, 2. And once I write that out, I can see that kind of makes sense. I can see that the second column is just a multiple of the first column, and the third column, well, it's exactly the first column. So they're not linearly independent. So a basis for the column space is just that one vector. Because there is one vector in the basis, I know the dimension, which again is another name for the rank of A, is just the number 1. In this case, the column space is a one-dimensional subspace of R2. All right, that really wraps up the last part of Chapter 2, our conversational vector spaces. Any last questions about vector spaces, basis, dimension, column space, null space? Any questions so far? All right. From there, we started Chapter 3. We started talking about determinants. Chapter 3 talked about determinants. We went pretty quick through this chapter. We basically focused on what we need to do to calculate determinants and then some key properties of determinants. So first, we need to calculate them. And to do that, we can use a formula for a 2 by 2, or we can use the row and column expansion for a larger matrix. And then we also had properties and theorems related to determinants. So number 2 says, here's my matrix A and my matrix B. Calculate all of the following determinants. You should really only have to do a full calculation for the first one, and there should be shortcuts or properties related to the rest. So go ahead and calculate all of these determinants, and when you're all done, put your answer to the last one, the determinant of A cubed, into the chat. So I know you've had enough time to work on it. Whenever you get through them, type your answer to the last one into the chat. All right, I'm going to start working through my answers here. So first, I'm going to calculate the determinant of the matrix A. All right, now to do that, so I'm going to write this as determinant of 1, 2, negative 2, 2, 0, 3, and 1, 0, 4. Now in general, I could do a row expansion along any row or column. And so as I move along whatever row and column I choose, there'll be a sign, there'll be a value, and there'll be a subdeterminant associated with each position. So if I moved across the first row, for instance, my signs alternate, plus, minus, plus, I would get plus 1 times a subdeterminant, minus 2 times a subdeterminant, and plus negative 2 times a subdeterminant. And the determinants are the determinant of the matrix I'm left with when I eliminate the row and column of my position. And once I do that expansion, I've reduced my determinant of a 3 by 3 to 3 determinants of 2 by 2s, and I could use the formulas for the determinant of a 2 by 2 to calculate this number. However, in going through that process, I have to calculate 3 subdeterminants. And I won't have to do that if the coefficients of any of these was equal to 0, because then I wouldn't care about the value of the subdeterminant. So the best practice is to always expand along the row or column with the most zeros. So in this case, my choice would be to expand down the second column. I do my signs again, plus, minus, plus, minus. In this case, as I'm expanding down that column, I'll get minus 2 times the subdeterminant, 2, 3, 1, 4. But then I would get plus 0 times something and minus 0 times something, and that would all go away. So all I would really have to do is this one subdeterminant calculation. In this case, I would get 8 minus 3, which is 5, times 2 is negative 10. So the determinant of A is negative 10. Any questions about that determinant calculation? All right, next I move on to the determinant of B. But the determinant of B, since B is an upper triangular matrix, the determinant is just the product of the diagonal entries. So 2 times 0 times 14, which would be 0 in this case. Next, I have the determinant of A times B. Our property here says the determinant of A times B is the determinant of A times the determinant of B. In this case, it would be negative 10 times 0, which would be 0. Next, we have the determinant of A inverse. Our property here is the determinant of A inverse is equal to 1 over the determinant of A. Now, if we apply that to the determinant of B inverse, well, in that case, we would get 1 over 0. And we can't do that calculation, right? Only Chuck Norris can. So that's a big NA here. And that also helps us, reminds us of one of our core properties or theorems about determinants that says if the determinant of a matrix is equal to 0, then the matrix is not invertible. So in this case, I can't calculate the determinant of B inverse because B inverse doesn't exist. Next, I have the determinant of 2 times A. This one's a little bit tricky. We'd like to say it's the 2 times the determinant of A, but actually it's not. If we multiply one row of a matrix by 2, that would double the determinant. But when we multiply the matrix by 2, we're multiplying each row by 2. Because when we multiply a matrix by a number, we multiply all the components by that number. So in this case, the determinant would be, well, 2 times 2 times 2 times negative 10. Right? In this case, that would be negative 80. In general, if we have an n by n matrix, the determinant of 2 times A would be 2 raised to the n power times the determinant of A. And then last we have the determinant of A cubed, but A cubed is really just A times A times A. And that way we can use our determinant of a product property to say this is the determinant of A times the determinant of A times the determinant of A, which would be the determinant of A cubed, which in this case would be negative 1,000. All right. A lot of calculations and properties there. Any question about determinants? Calculations or properties? All right. One more property. We already said that if the determinant of a matrix is 0, then the matrix is not invertible. But we could apply that to homogeneous equations. If I consider the matrix equation AX equals 0, I know there are solutions to that equation. I know x equals 0 will always work as a solution. So usually when I have a homogeneous equation, I'm interested if there are non-zero solutions. And it turns out that AX equals 0 has non-zero or non-trivial solutions if and only if A is not invertible. Because if A was invertible, we'd multiply both sides by the inverse, we'd get the only solution, which would be x equals 0. So we have other solutions only if A is not invertible. But we just talked about how that's related to the determinant. If A is not invertible, that tells us the determinant of A must be equal to 0. So what that tells us is that if the determinant of A is equal to 0, then there will be non-zero solutions to AX equals 0. And that relationship is very important as we calculate eigenvalues and eigenvectors. Our goal was to solve this equation, AX equals lambda x. And when we manipulated this equation, we could write it as A minus lambda I times x equals 0, and we wanted to solve this. But the problem is there was 2 unknowns and only one equation. I couldn't find both lambda and x. But I was trying to find the non-zero solutions to x. But what we just saw in our last theorem is the only way there can be non-trivial solutions is if the determinant of this matrix is equal to 0. So that gave us our steps. Our first step was to set that determinant equal to 0 and solve for the eigenvalues. After that, for each eigenvalue, we would solve the associated homogeneous matrix equation to find our eigenvectors. And then some of the value of calculating our eigenvalues and eigenvectors was that we could then factor our matrix A into either PDP inverse if we had real eigenvalues or PCP inverse if we had complex eigenvalues. So that's kind of the quick overview of eigenvalues, eigenvectors. Let's see if we can calculate the associated eigenpairs for this matrix and do the appropriate factorization. So go ahead and see if you can work with that matrix and factor it appropriately. All right, we'll do a little bit of a check-in here before I'll give you more time. But step one is to find the eigenvalues. So once again, we're trying to solve the determinant, taking the determinant of a minus lambda I, setting it equals 0, and solving for lambda. That means I'm subtracting lambda on the diagonals, and I'm calculating the determinant. So I take the product along the strong diagonal to get this values, minus the product on the off diagonals. From there, I distribute and simplify to get this polynomial equals 0. Then I'm finding the roots of this for my eigenvalues. I try to factor it, but I can't really see how to factor it, so I go to my quadratic formula. And when I simplify my quadratic formula, I have lambda equals 1 plus or minus 2i. Any questions about generating the eigenvalues here? All right, then my second step is for each eigenvalue, I need to solve the associated matrix equation A minus lambda I times x equals 0. So to do that, I'm going to subtract my specific lambda value on the diagonals. So I'm going to say if lambda equals, and I'm going to use the negative eigenvalue. Well, then I would have negative 1 minus the quantity, 1 minus 2i, 2, negative 4, and 3 minus 1 minus 2i, augmented with 0. I would do my row reduction on this using a little trick, and I would write my solution in parametric vector form to get my eigenvector. I'll be quiet here and give you a little time to wrap up. See if you can calculate the associated eigenvector here. If you get that eigenvector, you can type it into the chat. If you're stuck, you can type question mark as well. All right, I'm going to wrap up my calculations here. So after plugging in 1 minus 2i and then simplifying a little bit, I get to this stage. And now in theory, I need to do the row reduction, but I'm going to do a little bit of a shortcut here, right? The idea is that at this point, because I have a 2 by 2 matrix, I know these two rows are multiples of each other. Right? It's hard for me to see that because they're complex, but they're supposed to be multiples of each other. I've chosen lambda so that I know there will be free variables, so they must be multiples of each other. So because they're multiples, I could use the first row to eliminate the second row, or I could use the second row to eliminate the first row. I'm going to choose to use the second row to eliminate the first row, and then move the second row into the first position. So for a 2 by 2 matrix, I could go immediately from this step right to here. Now I'm choosing to work with the second row because I like to have a real number in the first component. It makes my row reduction easier. So from here, I can now finish my row reduction. I would take negative 1/4 times row 1 to get 1, negative 1/2 minus 1/2 I, 0, 0, 0, 0. Now I'm in row reduced echelon form. I'd write out my associated equations. I have x1, and then I'll add this number times x2 to the other side to get positive 1/2 plus 1/2 I, all times x2. There's no pivot in the second column, so x2 is a free variable. And then in parametric vector form, my solution looks like x2 times 1/2 plus 1/2 I and 1. Now, that would be a perfectly good eigenvector. There we go. And so I might write my eigenpair as when lambda equals 1 minus 2i, and I could write down that eigenvector if I wanted to. However, I also know that any multiple of an eigenvector is also an eigenvector. And so when I look at that eigenvector, I kind of hate the fractions, so I'm going to choose to multiply that eigenvector by 2 to write it in kind of a nicer form. 1 plus I and 2 in the second components. So I can multiply that eigenvector by a number to scale my fractions because I hate fractions. So that's my first eigenvector. Any questions about that first process? Please ask questions if you got them. All right, so I have my first eigenpair. Now, luckily with complex eigenvalues, I don't have to do that again. I don't have to plug in my other eigenvalue and calculate the associated eigenvector. Because the eigenvalues come in conjugate pairs, in other words, 1 minus 2i and then 1 plus 2i, it turns out the eigenvectors will also come in conjugate pairs. So this would be 1 minus I and 2. Note that the signs don't have to match though, right? They just come in conjugate pairs, right? All right, so now I've calculated my two eigenpairs. The last thing I can do is my factorization. Because I have complex eigenvalues, A should be able to be factorized into P, C, P inverse. Now the columns of P come from the real and imaginary parts of the eigenvector. To form my P and C, I only use one eigenpair. I only use the eigenpair associated with the negative eigenvalue. The real parts of the vector are 1 and 2, and the complex parts are 1 and 0. So I use the real parts of the eigenvector for the first column and the imaginary parts of the eigenvector for the second column of P. Now the matrix C in general has the form A minus B, BA, where A and B are the real and imaginary parts of the eigenvalue. More formally, if lambda is A minus BI, then this is the formula for my matrix C. Now because I'm starting with lambda equals A minus BI, that minus sign is kind of built in here. So when I compare it to my lambda of 1 minus 2i, I'm saying A is 1, B is positive 2, and my formula says that I should have negative my positive B value here. So that can be a little tricky, but the important thing to note is that if you use lambda, if you use the 1 minus 2i, the negative eigenvalue, your negative sign will always go in the top right component of C. Now once I have P, I could just calculate P inverse using my formula for the inverse matrix. This would be 0 minus 2, and this would be the matrix I get when I switch those values and change the sign on the off diagonal. So this would be the factorization of the matrix A. Any questions about the factorization P, C, P inverse? All right. Next, we're going to look at another case here. So given this matrix A, step 1 might be to calculate the eigenvalues. What are the eigenvalues for that matrix A? Go ahead and type the eigenvalues of the matrix A into the chat. All right, one quick answer, and that's absolutely correct. Instead of going through that long process, because we have a triangular matrix, the eigenvalues are just going to be the diagonal entries. So in this case, I would lambda equals 1, 1, and 2. Now, if I plugged in these eigenvalues, it turns out I will generate these eigenvectors. I've pre-done that calculation. And then I could do the associated diagonalization. If I want to factor A into P dP inverse, well, I get the columns of P are just the eigenvectors. So I'm just going to write in my eigenvectors as the columns of the matrix P. The diagonal entries of the diagonal matrix D are the eigenvalues. So I use the eigenvalues to form D and the eigenvectors to form P. Now in this case, I got fortunate because I had a repeated eigenvalue. I had lambda equals 1 repeated twice. Now the number of times the eigenvalue is repeated is called the algebraic multiplicity of the eigenvalue. Now when I plugged in lambda equals 1 to calculate the associated eigenvector, apparently I was able to get 2 eigenvectors from that one eigenvalue. The number of eigenvectors I get from each eigenvalue is called the geometric multiplicity. So in this case, the geometric multiplicity of lambda equals 1 is also equal to 2. And because those two values were equal, I was able to diagonalize the matrix. But there might be other problems where when I plug in that repeated eigenvalue, I only get one eigenvector. And so if those multiplicities don't match, I would say the matrix is not diagonalizable. All right. Any questions there? Now, once again, we're reviewing this relatively quickly because we're covering a whole semester's worth of content in basically 2 hours. So a lot of other stuff you can review there, but certainly the idea is to point you in the direction of where you may need more or less review. We're going to leave that be then for Chapter 5 and move on to Chapter 6, our most recent chapter, which talked about the dot product and the more general calculation, the inner product. So as we started this chapter, one of the most important pieces are core calculations. So for instance, given some vector u equal to, say, 304 and some vector v equal to 201, we should be able to calculate all these pieces. We should be able to calculate the dot product, we should be able to calculate the length of u, the distance between u and v, a unit vector in the direction of u, the projection of u onto v, and u perp. So go ahead and see if you can go through all these calculations. When you get through all of them, type your answer to the last one, the vector u perp, into the chat. Once you get your value for U perp, go ahead and type it into the chat. All right, we're going to go ahead and take a look here. We'll start with the dot product. So the dot product is taking the product of the components and adding them together. So I get 3 times 2, which is 6, plus 0 times 0, plus 4 times 1, which is going to give me a value of 10. So u dot v is equal to 10. And the idea is here is we're multiplying two vectors together in a way that ends up to be a real number, a scalar. So u dot v outputs a number, not a vector. Next, we're going to take the magnitude of u. This is the length of the vector u. Now, you might know from previous courses or the distance formula that we can calculate this as the square root of the sum of the squares of the components. So 3 squared plus 0 squared plus 4 squared, we would get a value of 5 here, the square root of 25. That said, in this course, it's really important to understand this calculation could also be thought of as the square root of u dotted with itself. The idea being here we can define length in terms of the dot product, which means when we generalize dot product to inner product in more abstract spaces, we can talk about the length abstractly in terms of the inner product as well. The distance between two vectors. So the idea is I have some vector u, I have some vector v. We measure the length as the distance between them as the distance between their tips. If we calculate v minus u, we would get the vector that goes between their tips, and the length of that vector, the length of v minus u, is what we mean by distance. So in this case, I would subtract the two vectors to get -1, 0, -3, and calculate the length of that vector as the square root of 1 plus 0 plus 9. So it looks like root 10 would be the distance between those two vectors. Next is the unit vector in the direction of u. In other words, the vector u has a length 5. I want a vector that points in the same direction as u but has a length of 1. And to do that, all I do is divide the vector by its length. So in this case, I would take 1/5 times the vector u. In this case, I would have 3/5, 0, and 4/5. This would be the unit vector in the direction of u. Next, I have a really important calculation, the projection of u onto v. So when we go back to our picture here, I'm going to rewrite my vectors here. I have the vector v on the bottom here, the vector u right there, and I'm projecting u onto v. So that means this vector in black right here, this is u hat, the projection of u onto v. And we can see that vector points in the same direction of v, so we expect it to be some number times v. In this case, our formula says u, right in red here, our formula would be u dot v divided by v dot v times v. All right, so the projection of u onto v is some number times v. There'll be a whole lot of v's in there and only one u. Now we chug out the calculation. We've already calculated u dot v to be 10. V dot v will be 4 plus 1, which is 5, and times the vector v. So in this case, the projection vector is 4, 0, 2. That projection is a really important piece. It's the vector on the line that contains v that's closest to u. It's the best approximation to u from the span of v. Sometimes that's exactly what we want, so we calculate the projection. Other times, we're very interested in finding this perpendicular vector, which we call u perp. To calculate u perp, we just take u minus the projection to get that perpendicular vector. So in this case, we would take u, the vector 3, 0, 4, minus our projection vector 4, 0, 2, and the result should be -1, 0, 2. This should be our u perp vector. Now I'd like to be able to check my work so that I know that I'm correct before I enter my answer into infinity on the exam. So what would be a great way to verify that my UPerp was probably correct? What calculation could I do? Go ahead and type that into the chat. What calculation could I do to verify my UPerp is likely correct? All right, I see an answer in there. It says UPerp times V. I'm going to assume that times means dot product. So I would say UPerp dotted with V, because I know that those two vectors are perpendicular. So if I take UPerp dotted with V, I better get 0, right? Because two vectors are orthogonal, they're perpendicular, if and only if their dot product is equal to 0. So I have my UPerp, and I'm taking the dot product of that with V, 2, 0, 1, and sure enough, I get negative 2 plus 0 plus 2, which is 0. So that's a nice way to confirm that my answer is correct. Okay. So the idea again here is that through dot product calculations, we can determine the length of a vector. We can also determine if two vectors are orthogonal. That gives us kind of a sense of angle to our vector space. And we can also calculate this projection thing. That means if we want to add a geometry, right, a length, a orthogonality onto an abstract vector space, we could do that in terms of dot product, or the more general calculation, inner product. So now I have some inner product calculations here. So if I'm in a matrix space, in other words, consider the vector space that is the set of all 2 by 2 matrices, right? So in other words, A could be some matrix 1, 2, 3, negative 1, and B could be some matrix 0, 2, 3, 4. These would be two vectors in my space. Now to do these calculations, I need to define what you mean by inner product or dot product on this abstract space. So I'm going to have to provide a definition for that. And there are many different definitions that could be acceptable. In this case, I'm going to give you an example definition that says to calculate A inner product B, the arbitrary inner product of two matrices, I would calculate the product of their components in the 1, 1 position plus the product of their components in the 2, 2 position. So I'm multiplying the values on the diagonals and adding them together. So with that definition, see if you can calculate all of these same things, but now in terms of this inner product. For this problem, once you do your calculation, type your answer to the first one into the chat. What is A inner product B? Just type your answer to that one in the chat. Calculate A inner product B and type your answer just to that piece into the chat. And if you're stuck, feel free to type in question mark. All right, let's take a look. All right, so our definition of inner product is this, and this says take the number in the 1, 1 position of A, so that would be 1, times the value in the 1, 1 position of B, that would be 0, plus the value in the 2, 2 position of A, and that would be negative 1, times the position in the 2, 2 position of B. That would be 4. So A inner product B would be 0 minus 4, or a value of negative 4. Oh, and there we go. And this fits our idea of dot product. I've somehow multiplied A and B together, and the output is a real number. It's the number 4. So that's our calculation for A inner product 4. I'll do the next one here as well. Here I want to find the length of A, the length of a matrix. Boy, what does that mean? Well, now we can define length in terms of inner product. Normally I would say it's the square root of A dot A. That's how I would define it if these were vectors. And I can kind of think about it in terms of vectors, but because I'm an abstract space, instead of dot product, I really mean inner product. So I say A inner product with A. Now to do this calculation, it's the square root of A inner product A would be A11 times A11 plus A22 times B times A22. So in this case, it would be this guy times itself plus this guy times itself. It would be 1 plus 1, or the square root of 2. So maybe before today, I had no idea how to talk about the length of a matrix, but now I have a definition that allows me to calculate that. Okay? And all of the rest of the definitions, the distance between the two matrices, a unit vector, the projection, I can basically start by writing out my formulas in terms of dot product and then change all the dot products to inner products. All right, now I'm going to be quiet for a little bit and see if you can finish off the rest of these calculations. All right, I have my calculations up here. I'm going to just display them, have you check your work, and let me know if you have any questions about any of these individual calculations. Same process we did with dot products. I'm just replacing the dot products with inner product in this abstract vector space. Any questions here? All right. Next, we're going to get into a couple applications of dot product and projection. And we have these core applications. One, the determinant of vectors are perpendicular. Right? If we check the dot product, see if it's equal to 0, that's a very important application in itself. But our next application is given some basis, we might want to use it to find an orthonormal basis. An orthonormal basis is much easier to work with than a traditional basis. So sometimes we want to create one. The next application is to find the QR factorization of a matrix. And then the last one is to find the least squares solution to AX equals B. In a case where there is no solution to AX equals B, we want to find the best approximate solution to that matrix equation. And really all these revolve around the idea of projection. And we have a little progression about our idea of projection. So far we've talked about projecting one vector onto another vector. So if I want to project y onto v to calculate that projection vector, I know how to do that. I have y dot v divided by v dot v times v. I also know that I can use that projection to calculate my y perp. But now if I want to go on to projecting onto a space, not just onto a vector, I basically have a repeated process of that. But the important thing is to start with, I need an orthogonal basis for w. I can't use a regular basis. I need an orthogonal basis. But then if I want to project w onto the space to get my y hat, it's basically the projection onto each of the orthogonal basis vectors. And then of course, if I wanted to calculate a vector perpendicular to a space, I would just take my y minus my projection, just like I did with the regular vector. And now the idea is I can even extend this into abstract spaces, not just some plane in R3 or R4, but now I can talk about projecting a function onto a polynomial space, an abstract space. And to do that, it's really the same formula I used for projecting onto a regular vector space, but now I'm changing all of my dot products to inner products. Once again, I need an orthogonal basis for my abstract vector space W. Then I would project onto each basis vector and add them together. But now those individual projections would be defined using whatever inner product I'm using in the space. But the image, the graphical representation, is pretty much the same. I'm projecting my y onto my abstract space to get y hat, and then if I want to, I can calculate my y perp as y minus y hat. So that's really the progression of this. So to do this, though, I need to start with my orthogonal basis. So one thing might be, given this basis for a vector space, find an orthogonal basis. So first, if I wanted to check to see if this was orthogonal, what's my calculation to test if it's orthogonal? Go ahead and type that into chat. If I called this one U1 and this one U2, what would I do to determine if they were already orthogonal? Absolutely, the dot product. So I could calculate U1 dotted with U2, I would get 2 plus 0 plus 4, 6. So these two vectors are not orthogonal. So now I'm going to do my Gram-Schmidt process to create an orthogonal basis. Now to do this, I basically got my picture. I got my U1 and my U2. And I'm just going to start with one basis vector. I'm going to make U1 my starting point. My goal will be to calculate an orthogonal basis, V1 and V2. I'm going to let V1 just equal U1. It's my starting point. Now I need a vector that's perpendicular to V1. To do that, I'll project u2 down to find the projection, and I'll subtract to get this perpendicular vector. So this vector u2 minus the projection of u2 onto v1 should give me this perpendicular vector. And that's my formula for v2. u2 minus the projection of u2 onto v1. And if I had more vectors, I could continue to extend this. If I had more vectors, my v3 would be my u3 minus the projection of u3 onto v1 minus the projection of u3 onto v2. And that formula grows with the Gram-Schmidt process. I will give you a head start. See if you can calculate your orthogonal basis for this vector space. I'll give you a head start, and then I'll start quietly working through my problem. All right, I have my calculations up here. Once again, I just started by letting v1 equal u1. And then to calculate my v2, I had u2 minus the projection of u2 onto v1. From there, I always tend to write out my definition of projection, just so I can see all the calculations I need to do. And I just started to chug it out. In the end, I got v2 equal to -1, -1, -1, 1. And I wanted to make sure I was right to see that if I really had an orthogonal basis. So I calculated the dot product and I got a value of 0. So they were orthogonal. So this becomes my orthogonal basis for V. Any questions here so far? All right. Now the next question I have here is to find the QR decomposition of a matrix. Right? So we need to take a matrix A, so this would be my matrix A, and factor it into a Q times R. Now, all I need to know is really the definition of Q, and that should tell me what to do. And it turns out the columns of Q form an orthonormal basis for the column space of A. So, the column space of A is the vector space I can build with the two columns of A. Now, because my two columns are linearly independent, a basis for the column space would be 1, 0, 1 and 2, -1, 4. However, I need an orthonormal basis. So I need to take my two columns of A and use Gram-Schmidt to find an orthogonal basis, and then further find the unit vectors to make an orthonormal basis. So I've really done some of the hard work in the previous problem. I've now taken these two columns essentially as my basis vectors u1 and u2, and I've calculated an orthogonal basis v1 and v2. But to form the matrix Q, I now have to figure out what the length of V1 is. In this case, it would be the square root of 2. And what the length of V2 is, which would be the square root of 3. And then the unit vectors would be V1 divided by its length and V2 divided by its length. So that means my matrix Q would look like 1 over root 2, 0, 1 over root 2, and negative 1 over root 3, negative 1 over root 3, and 1 over root 3. And these will always tend to be kind of ugly because I'm calculating unit vectors. So to find the columns of Q, I use Gram-Schmidt to find an orthogonal basis, and then I normalize. Now that makes Q an orthogonal matrix because its columns are an orthonormal basis. And that means Q is pretty special. It means that the transpose of Q kind of acts like an inverse. Turns out Q transpose times Q is equal to the identity matrix. And this is going to help me find my other matrix R. Since I know that A equals Q times R, and I know what A is and I know what Q is, I need to solve for R. And so to solve for R, I'm going to multiply both sides by the transpose, and because Q is a special matrix, this will simplify to identity. And it turns out that R is really just equal to Q transpose times A. So I'm going to write down Q transpose, which will be 1 over root 2, 0, 1 over root 2, and negative 1 over root 3, negative 1 over root 3, 1 over root 3. And I'm going to multiply it by my matrix A. Now this calculation looks pretty ugly, but as long as I haven't tried to oversimplify any of my denominators, the multiplication is really not too bad. So in this case, if I took this row dotted with my first column, I'm really just going to get the square root of 2 as the common denominator and 1 plus 1 in my numerator. I'll then move down to take the second row dotted with that first column. And here once again, I'll have square root of 3 as the common denominator, and I'll have negative 1 plus 0 plus 1, which is going to give me a value of 0. And I'm really happy that that's a value of 0 because this matrix R is supposed to be an upper triangular matrix. I will then move on to using the second column of A. I'll get 2 plus 0 plus 4. I'll get 6 over root 2 here. And then in the last component, I will get negative 2 plus 1 plus 4, which is going to be 3 over root 3 here. And that would be my matrix R. So I found Q and I found R through the QR factorization. All right, long problem. Any questions here so far? All right, one last piece to cover here. Hopefully my Microsoft OneNote will hold out. There we go. And it's finding the least squared solution to a matrix equation. So here I have an equation AX equals B. And normally if I want to solve this matrix equation, I would do an augmented matrix and do row reduction. And I could certainly try that. You don't have to do these calculations with me. I'm going to write them out kind of fast. But if I tried to set up my augmented matrix and do my row reduction, I would come over here and I would go 1, 2, 1. I would do row 3 minus row 1. I would get 0, minus 2, and 0. 0, negative 1, negative 1. I would probably multiply the second row by negative 1. And then I would do 1, 2, augment it with 1, 0, 1, 1. I would do row 3 plus 2 times row 2, and I would get this. And so this would be my matrix in REF form. From there, I'd identify the pivots, and I see that there's a pivot in the far right column. Once I see that, it tells me there are no solutions to this equation. And normally in chapter 1, we would just be done. We would say there are no solutions. But now in chapter 6, we can say, well, since there are no solutions, let's find the next best thing. Let's find the best approximate solution. Okay? And the concept is this. The concept says, well, if I thought of the column space is a vector space, a subspace, I know that the vector B is not in the column space because there's no solution. So instead what I'm going to do is take my vector B and project it onto the column space to calculate my B hat. Now, since B hat is in the column space, I could now solve AX equals B hat to find my best approximate solution. I could certainly go through that process. However, that process would be really challenging because to start with, I would need to have an orthogonal basis for the column space. That means step 1 would be doing Schmidt, that whole long process, just to find an orthogonal basis. From there, I'd have to do the calculation, that's the projection of B onto the column space. Right? So that's a whole projection calculation. Even after doing all that, I would still have to solve the equation AX hat equals B hat to find my least squared solution. Okay? So that's a long process. Now the nice thing about that process is I can write all of those steps in terms of inner product, so I could really generalize that to any space. However, if we're working with a nice matrix equation and nice vector spaces, we can shortcut that and do a different calculation instead. Instead, we can just multiply through by A transpose and solve A transpose A times X equals A transpose B instead. This is called the normal equations, and the solution to the normal equations is my least squared solution. Okay, so instead of going through that long process, I can multiply through by A transpose and solve that instead. So my steps would be to solve A transpose A X hat equals A transpose B for my least squared solution. That would be the best approximate solution. And then since it's not the exact solution, there'll be some error. And it turns out to calculate my error, I would first calculate B hat, which would be my A times my X hat, right? And then the difference, the distance between B and B hat, would equal my error. So that's the recap. The last thing we're going to do is we're going to practice on this problem, see if you can calculate the least squared solution to this matrix equation. All right, I know we're getting to the end here, so I'm going to power through this. I basically wrote out my equation with my transpose matrices. Now I'm going to do this multiplication. When I do that multiplication, I'm going to get 2 and 2. And then I'm going to get 2 and 4 plus 1 is 5. On the right-hand side, when I do that multiplication, I'm going to get 2 and 3. And I need to solve this matrix equation instead. So that means I'm just going to set up this augmented matrix and do my row reduction. I'm going to take row 2 minus row 1 to get 0, 3, and 1. I'm going to divide the first row by 2. I'm going to divide the second row by 3. And then lastly, I'm going to take row 1 minus row 2 to get 1, 0, 2 thirds, and then 0, 1, 1/3. So it turns out my least squared solution will be 2/3, 1/3. So that's my least squared solution. Now if I take my matrix A, my 1, 2, 0, negative 1, 1, 0, and I multiply it by my least squared solution, I will not get B. I'll get the thing that's closest to B. So when I do this multiplication, I'm going to get 2/3 plus 2/3, which will be 4/3. I'll get negative 1/3, and I'll get 2/3, right? This is my B hat. I couldn't get to this B, but what I got to was the closest thing I could get to. So now my error is going to be the distance between B and B hat. So that means I'm going to take the length of the difference between them. So now I'll take my B hat. I'll take my B hat and subtract my vector B, which is 1, negative 1, 1. And I'll take the length. So this is the length of the vector 1/3, 2/3, negative 1/3. And when I calculate that length, I'll get the square root of 1/9, 4/9, and 1/9. I'll get the square root of 6/9. And that would be the error in my least squared solution. All right. Make that a little bit bigger here. See if I can fit that all on one screen. Questions? Any questions about least squared solutions? All right, just under 2 hours here. That really wraps up the entire review session. That is all I got. If you have any questions, you continue to prepare for the exam, feel free to email me, reach out, put something on my calendar. Otherwise, the first window opens up on Sunday. There's more testing times on Monday and Tuesday. I made a recording of this review session, so after about an hour or so, once everything's processed, I'll try to send out the email with the finished notes and also the link to the video. If there are no other questions for me, you guys are free to go.